Okay, today we try to sneak up on mechanics as far as force goes. We haven't mentioned that yet. Everything's been done just with momentum conservation, and then with time reversal, we've got energy conservation. We've proved that. Now we're going to make use of it to develop the concept of force and pressure and all that kind of stuff. But in a very simple system, it will still be a one-dimensional one single degree of freedom for each mass that we deal with, but the basic idea of making a force field out of many small bounces is a cool thing to think about. And of course that's what you learn first of all in statistical mechanics or thermodynamics, that the pressure is due to things being, in that case, many particles, 10 to the 23rd times whatever number moles. So here we're going to make it really simple. It's going to be basically one particle providing pressure. But it'll be a very small, fast one, so it works. We'll see how that goes. So the basic thing I want to do after we've gotten that little game going is then introduce the idea of the potential. And that's what's so cool about the way we're presenting, is that's immediate. I do want to make a distinction between what a physicist and a mathematician does. That's kind of interesting to know. And then the rest of the lecture is some sort of sketchy stuff that's trying to get a little bit of our formalism and thinking and phenomenology of quantum mechanics, and the analogies between the classical stuff that we're doing here and quantum mechanics, I think, are worth knowing about. So let's go through it. And remember that the beginnings of every lecture here has these links to various things. Some are very interesting. Now the one thing that I think you can see how we're going here with these two pictures here is that when we had a mass ratio of 49 to 1, it took quite a few bounces to turn this around. Well, that's what we're going to do today. We're going to analyze the case here in the limit of very high mass ratios or very high numbers of bounces. And the idea of this starting out and going bing, 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 bing like that, as it works its way around the ellipse, is going to be happening in the collisions that we show. It's just it'll happen so fast that you won't really see it unless you're looking for it. So let's get started here with just the basic idea of how it is that we would handle just the force that occurs. We have a fairly large mass here, and then a little one going back and forth. So this will be the gas. If we were thinking of a one-dimensional model of a gas, here's the gas, and here's the piston that's much higher mass. And the idea is that if you start with this thing having a large distance and just go and move it yourself the effect is going to be to make this one go much faster. So as we go from cool to hot, that's the effect of making the space that this thing has to travel smaller, but at the same time, each time it bounces, it picks up a little speed. So this is kind of what I would refer to as a double whammy. So in this case, and by the time it gets going fast, there's really two things that are going on here. First of all, at this point we have a longer time between hits, and we have a lower velocity. Both of those change. The time gets shorter, the velocity gets higher. So shorter time and higher velocity means, I guess that's a sort of a New York expression, double whammy. means you're getting hit from both sides in some way. And that's definitely what's happening to the force laws. So we're going to discuss the force laws that you get for a case when you don't really get too much of an increase in velocity, or any at all. We'll call that orthothermal. We'll imagine that somehow this wall takes away the velocity that this ball has given it, and just always comes back on the average with the same velocity. That is one extreme of the force law that we're going to be talking about. And the other extreme is the one where everything is going, a double whammy is occurring. So, I will go ahead and begin the analysis that we need in order to understand this. And is write an equation that makes sense just using what we have already developed, and that's the conservation of momentum and kinetic energy that results from that if the time reversal symmetry is present. So, you might say that we have a new axiom at this point if we make the statement that the force would be the change in momentum with respect to time. I say that's not the case. This is simply a definition, not another axiom. This is just something that we notice from looking at these collisions that we've been doing so far. So we will just define momentum per second as a force. I'm still not using MKS units. We'll get around to that soon enough. But the idea of a change in momentum, and that is the change that occurs from in to fin in a collision, each collision, that is the momentum change per bang, and then multiplying, or I should say dividing by delta T, multiplying by 1 over delta T. That's the delta T is the seconds per bang, the inverse of that frequency, the bangs per second. So that's what we're multiplying the number of bangs per second times the momentum per bang, and that gives us momentum per second, which we will define to be the force, which is shouldn't be anything new to you that have studied all of this in a normal way of presentation. This is a weird way to present all of this. I think it's cool. Anyway, one of the things that we probably didn't make too big a fuss about, but when we have these very skinny energy ellipses with the M1 much greater than M2, the 49 to 1 is the biggest we have looked at so far. We'll do some more today. The idea is that on each of these collisions, the ball is increased by twice, and this is an approximation, but an approximation when you have the masses so different. The large ball has a certain velocity v1, and the increase of the velocity of v2 is in each step here exactly 2 times that velocity of v1. Okay, so that's the key thing that we're going to make use of. So for this extreme case of a large M1, the V2 final is very close, very good approximation. In fact, this is an exact for each collision. The sum of the twice the velocity there, and without the absolute signs, this is the relation that we're looking at for this case, as this ball moves in on that the little v2. Now, the change in momentum, this being momentum per bang, and this being bangs per second, is the thing that we need to evaluate for the case M1 much greater than M2. So that's what we'll do here. The basic assumptions that we're making here is that we replace V2, this V2 right here, with that combination, the n minus twice the velocity. So we end up with a thing like that, and then we make a couple more assumptions here. We assume that the mass m is moving fairly slowly, so that I can neglect the what I can do is I'm assuming a slow m1, and that v1 is much less than v2. If that's the case, then what I can do, if I got this right here, is just write this thing as approximately, forget this thing right here, just approximately equal to that 2v2 times m2, 2v2, coming from this relationship right there. So these are the, this is the thing that makes this a fairly simple result. That is, we come up here then with a 1 over del Q with a V2 in it, divided by the distance of the travel from back and forth in one bang. And then you've got the change in momentum, which is twice the velocity and of course times the mass. So you end up here with something that you should recognize that we've already derived, and that is the kinetic energy is 1/2 of an m2 v2 squared. So the kinetic energy of this protagonist, this poor little m2 that's going to be slowing down or speeding up if we're going the other way, the big m1, the kinetic energy is proportional to the kinetic energy, inversely proportional to the space that remains between the two, in which the m2 is able to go back and forth. So this is very similar to the introduction of statistical mechanics from thermodynamics. In any case, what you get is a force law, a law in which the force that you're feeling here, that's the amount of momentum that's being transferred to this m1 right here, the delta p delta t, is a function just of the distance they're separated by. And that's assuming that the kinetic energy is a constant. That is, that the V2 has not gained much energy. Something has to be in the walls. This is the isothermal thing. The wall serves as a thermal bath to keep M2 cool. It's one way to say that. So this guy has moved in now and has experienced the momentum of the collisions, but it hasn't had the double whammy. This is the single whammy. So this guy is always coming back with the V2 that he started with. And so that's a pretty easy derivation right there for that part of the story, the part that I'm calling isothermal, using a blue color to represent it. Okay, let's keep these things up to date. Now the next step is to do the opposite sort of situation where we don't assume that the wall is keeping things cool here. And when we do that, we get a little bit more complicated expression for our force that is going to be derived right here. So, if that, and now remember, we were doing this stuff turned on its side. We had a ceiling. We didn't talk about gravity at all in any of the simulations we've done so far. That's for the later. But well, now I've turned it on the side, which makes it more like an air track experiment. And we basically have the idea here, that's just from what we had before. The bang rate, b, is the velocity divided by the distance there, and the 2v is what it picks up each time. So now we're letting v2 to grow. The change in v2 is definitely not going to be 0 in the ideal collisions in which the energy isn't taken away by the wall. So this particular equation simplifies very nicely into just a logarithmic equation, and that makes it possible for us to write an equation for this. Now, this this particular logarithmic equation is very nice. It's one that tells us that if I'm done integrating those and getting a logarithm, right? Logarithm is this is a shorthand notation that you see on a keyboard. The basic idea is to integrate both of those, get that, and so what you get then is that the logarithm of v2 is the logarithm of the inverse of y. Okay, so the v2 here is going to be going up as y compresses by this thing. Now we just have to figure out what that constant is, and we've got a way to make a pretty clever little demonstration of the effect of this thing. So the basic force law that we're going to be getting is going to involve a V2, this V2 right here, and that is going to be inverse with y. It's going to be constant like it is up there. And so when you put those two together, then you get something that goes up with not the distance y in the inverse, but the distance y cubed, the distance cubed in the inverse. So pick an initial velocity as an initial time and call that a constant, includes the mass there. But basically the force is a inverse third power as opposed to just inverse single power. So that is what we're going to be working with. Then compare these two and talk about the various things that happen. Now, the application of it comes later. This is a link that you can jump ahead. We're going to get to that, and we'll jump back and forth between these results here and differential versus integral ways of looking at these the forces. So this sets the stage for what we really want to do today, and that is make a force field and a force potential. So that's the situation. This is the trick right here. This is the main trick of this whole scheme that I'm talking about here, is that we already have very clearly shown in these collision experiments that if time reversal is okay, then this is a constant. This is kinetic energy, but we'll just call it the total energy, and then we'll replace this. This is the double whammy. This is the most spectacular of the two choices. This one is totally a function of y, and that's the potential energy. So we know that the sum of these is always a constant, and we have shown that this is that. So we're off to the races on this. So this is where we have a potential energy that's describing a force. Well, we have to check that this actually works, that it jives with our basic definitions of the idea of a potential. So I need to connect that. I have to relate that through a work relation. Now, the thing that you always worry about when you're trying to do things in a super logical way is, have I got another axiom here? Have I just picked up another axiom? What's our axiom baggage count at this point? And I say, no, this is not another axiom. This is something that we already mentioned to you on page 50 of this textbook, where we do the little calculus trick. So the answer is no, it's not another axiom. It involves a very simple calculus trick. This is the integral version of that. And then the second row here is the differential version of that. This is a very clever little piece of calculus that every person who starts mechanics should be aware of. The idea that the force, the rate of change of momentum, you do an integral of that over the distance in which this is all being done, that you get here, this thing here, the P dp dt And a dy, we can just do a dy dt and dp. That's kind of a little sneaky switcheroo there, but mathematicians would rip their hair out of jumping to that without doing the del epsilon proofs and all that. But anyway, it boils down to an integral of velocity with respect to momentum. That is an integral of v with respect to the differential of mv. Well, that's mv squared over 2 plus the constant. Okay, that's the integral thing. The differential one's the same idea. I just look at the force times the velocity. That is the force as a change in momentum times the velocity. And then I know that that's a dmv. So once again, I get a derivative, a differential of mv squared over 2. And that's the time derivative of this thing we call our potential. Okay, well, enough trickery. Let's just see how it plays out and if it makes sense, because the differential part description of this and the integral description of it have to match. So we need to check that that's indeed kosher, as it were. But at this point, I should indicate that we're going to be seeing two possibilities for the sign that we use in the relationship between force and the derivative of potential. You have a plus sign, and that's the traditional one right there. That's the mathematicians. Mathematicians are the ones that got this all going. Potential theory is very much a piece of mathematics, more so by, I would say, far than the physics, because there wasn't much physics that was available to look at all of the complicated potentials the mathematicians were talking about. As they developed the theory of complex variables, which is going to be our chapter 10 of our unit, we'll be coming back to this. And at that time, we'll use the traditional one because it doesn't have a minus sign here. Now, what's the deal as far as just the sociology of mathematics versus physics? This is a little bit off color, but the basic idea is the mathematician, you've heard of the constipated mathematician, they hold it back. That is, they're talking about the amount of force it takes to hold this thing at that certain point. They're not thinking about motion that much. They're just using that as a way to think. If that's the case, then it's a plus sign. That's what you're going to call your force, the one that goes this way. But if you're a physicist, you're thinking, that's the force I want is the force that nature is giving me here. Just let it go, okay? That's the physicist force. It's got the minus sign on it, okay? Just the opposite of the mathematician. But the mathematician is more elegant because having a minus sign and minus plus, you got an annoying minus sign. You don't have it here. So when we go to the complex variable stuff and do the fields associated with complex functions, we'll always use the plus sign just to keep the minuses out of the picture. But be aware that the physics is the same regardless. It's just the formalism is a little neater if you do it the old-fashioned way. So potential field theory really belongs to the mathematicians. They are the ones that got this going. Okay? Now the question is this consistent, which is something back on page 22 here, with our a force of 1 over y cubed relationship? Does that make sense? Is the integral of that force going to be giving us the right result up here? So we look at that and ask, is that force consistent with minus the derivative of the potential? We'll use that in most of our physics for our course. We'll certainly be putting a minus sign on every derivative of a potential to get to force. But be aware, the plus sign is lurking in the historical background. So we're asking about this, and sure enough, the derivative of this thing, that is, the derivative of all the numbers that we need here, of that is a y cubed. So that is definitely, and I'll just click real quick here on this one to get back to that link there. I say, yes, hurrah for this. Excuse me, I'll do it on this screen right here. make sure that it works. Let's just see if this works. This is where we talked about the y cubed, okay? So we're back at page 34. I can, go back and forth between these two. And be aware we're going to do more of this just to make it easier to look things up in complicated derivations of the lecture notes. So lecture notes are going to have that convenient piece of thing that a textbook doesn't have. You see, we're going into the electronic age, so you might as well try to take advantage of it for making reading things easier. Anyway, that's why I say we have here a perfectly good theory associated with the more difficult of the two cases, and that's the adiabatic, non-diabatic. Adiabatic means not. What does that mean? It really means not gradual. This is the kind of force law that you need to use when things are happening quickly. So if you're attacking a system and pushing quickly the parameters of it, not letting it settle and equilibrate, you're talking about not gradual. That's not diabatic, but adiabatic. Okay, a lot of terminology that is really confuses people pretty easily. Okay, so we've got that, I think, under control. We can go back and look at what the situation would be here. Let's see if I jumped, and now I'm going forward, pushing all the buttons to get to this particular point right here. If the force is that inverse y, which is a simple case, this is a single whammy now. There's something there that's keeping the V2. The little ball is doing all the work of the gas, or whatever you want to call the thing that's giving the force field. Okay, this is a single whammy. It's only changing in its rate of bangs, number of bangs per second. Just a few, boom, boom, when it's big, and then boom, 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 when it's smaller, but always the same boom. It doesn't get any increase in V2. If that's the case, that's a little bit different force law that we have here. We have here now an integral of that thing, and that's a logarithmic potential. That's kind of cool. I mean, let's just plot the logarithm and see what it looks like. It's going to be a nice thing coming out. It's not like inverse cube at all, and not only that, but it comes here and it just snuggles right up to the y-axis. Okay, well, of course, that's if you turn your head to the side, that's an exponential right there, right? And exponential dies against the thing here, so be aware of this geometry. Okay, that's the thing that's kind of neat. Anyway, we're getting a potential here, still proportional to kinetic energy, but its spatial dependence is this logarithm. Okay, so this is the other side of this story I'm trying to tell you here about these things. So the actual force law, the 1 over y, here, of course. That's an algebraic expression. It doesn't hug axes at all. But it's the kind of geometry that we're going to be working with. Now later on, when we do the complex force field for a monopole and have this thing here, and of course this would be in 2 dimensions, so this would be an exponential curve over evolution, sort of a flower, you might say, a morning glory, but with a very narrow whatever they call the inside of a flower. That is the situation that we will be dealing with at that time. That's coming up in chapter 10 of this unit. Okay, so here we are with the same situation. 1/2 m1 v1 squared plus 1/2 m2 v2 squared, but it's all snuggled into that particular logarithmic function that we're dealing with. And we're doing this for a very large mass compared to the little one. So all of this is true whether we're dealing with a logarithmic force or this much hotter double whammy adiabatic force. It's still going to work for this one, and we better make sure that it does. So hurrah again, that is definitely what results from this. Okay, so both of these are fair game for this very strange way to treat force fields. And I don't think there's anything else that I need to say except that, but let's use it. Let's go ahead and see what it can do, and we'll simulate. We'll actually run a little simulation where we have a single ball but being hit from both sides and being given either a single whammy or a double whammy. We'll do the single whammy first. I think that's the easiest one, and then I'll give you the double whammy for you as an exercise in problems we hand out on Wednesday. Okay, fair enough? Nobody looks too happy about that. It's kind of a fun problem, all right? But we'll see the results through the simulation that we do right now. And we'll be doing it with the isothermal. Well, at least I'll be talking about it with the isothermal. That's what I've got here on these two screens here, to copy the screens. Now, basically the idea is, and this is some algebra that you should never forget, what we've got here is a force of inverse y. Okay. So the y in this case is either 1 plus x or 1 minus x. We're talking about the, if this thing is a little bit off center, the idea is that it's going to make this side hotter, I should say make the speed higher. It's not going to necessarily make it hotter. If we're doing isothermal, it's not that it's getting hotter, but it's going to have higher speed. So there'll be a high pressure on this side as you move this way, a lower pressure because you went away from this ball, and then as you bring it back to the center, then you'll have medium speeds of these balls, but presumably equal. So we'll imagine that we're at the very bottom of the potential, but these are the potentials that are summing up to make that potential. So we've got a logarithmic fall off here, a logarithmic fall off there, giving us a well, a potential well. And that's what we want to explore. That's what we'd like to play with, just to get this basic idea actually doing something. So what we do is we write out these two things. Now, the binomial expansion that we're doing here, 1 plus x to the minus 1 power and 1 minus x to the minus 1 power. Most people have worked with that enough times that you recognize that's just a sum of powers. This one is an alternating sum of powers. Now, to see that, of course, it really helps to go ahead and just write the thing out using the binomial theorem. So this is a more complete and descriptive notation that we're talking about. There's a y0 that's a constant here, and we're going to have plus a little bit of x, minus a little bit of x. So x is going to be fairly small. It's something we can expand the force law around x equals 0. So x equals 0 is when the ball is right in the center. As it moves out a little bit, but just a little bit, it's already going to feel some pretty big force, big enough to make the thing move. So binomial theorem of anything to an nth power is that, and this particular minus 1 power gives you the force law series, a series that this is going to be. So you're going to have this series right here, in which you have alternating minus, plus, and then the one over the thing with a minus sign has all pluses, okay? And there's a bit of cancellation that's going to help us here with that. So there we are, and there's the cancellation. Cancellation of this term right here, 1 over y0, is gone, so that's out. But this one does not cancel, okay? So you're going to have to deal with that one. You're going to have something that's linear divided by y0 squared. You see this one has a minus sign here, it has a plus sign here and minus there, so there's two minuses, you're going to have that. And then the next two, those cancel, but then if you're worried about something to the third power, that's what we call anharmonicity, this would be a harmonic, this will be anharmonic, then that will not cancel. So you'll get two of those things, and so forth. So that's the what we're dealing with here. And in the limit that x is not too big, and that's what we're going to do a lot of in this class, because things become analytic only if you make approximations of that sort. This is still analytic, but this is a complicated thing. This is going to be a harmonic effect that results according to if you believe the isothermal theory that we propose here. So we're going to get a force that's negative of x, so that means if I move x out, it's going to want to come back. You kind of see that that's the potential. You're in a potential well, so it's a restoring force. And then you're going to get a minus something with x cubed if x gets much larger. So there'll be a little bit of an extra perturbation to this if you make x bigger. Okay, so far so good. This is what I'd like to simulate this, at least make an effort at it. Now, before we go on, this is our first talk about a harmonic oscillator that's worth mentioning. This spring constant here, 2, and then the coefficients that we've chosen for this, and that depends on the kind of the initial velocities that you have and the initial spacings that you have. The thing is this combination right here, and there are the variables that are determining that. That is the spring constant of this thing, and that's the other thing the mechanics class, including this one, makes a big fuss about. Every system that we talk about, the only things that we can really solve easily are the ones that boil down to harmonic oscillators at some level. The other solutions involving more complicated force laws than proportional to the distance. It's simple Hooke's law, force law, that's what kx really represents here. Those are few and far between, but almost everything has got a harmonic approximation, so we'll be doing a lot of that during this class. Now, the oscillator force, the harmonic Hooke's law force, and there's the derivative expressed with that, and then the potential that goes with that, okay, are here, and then there's the frequency. Now this is all stuff that you've known before, but let's just express it in the simplest possible way. And the way to do that, which I find very, very instructive for if you're going to be teaching sophomore physics and this comes up, this is a quick way to see that if your total energy is given as, well, good old mv squared, that's kinetic energy. Now we've got a potential that's got a y squared in it. Okay? If that's the case, then you discover that this particular function, a good old sine, or a derivative involving cosine, that goes together in this kinetic energy thing to sum up to 1 times a constant. So this is the total energy of this oscillator for all time. And that is about the simplest as I can get for deriving something like that. We're not having to go through this differential equation technology at all. This is just simple calculus of trigonometric functions. So, the basic idea of having a frequency that is that spring constant divided by the mass of the victim of being hit by balls coming from both sides, that is what we need to see here. But it seems kind of crazy that this thing would behave like a harmonic oscillator when you really get down to it, because, my gosh, it's being hit really badly on all sides, and that is not an easy thing you would think at first to solve. But this is where it will come up. So let me go ahead and just reverse these screens here. I am going to simulate with that one, and I will leave this one here just as a reminder of what it is that it's supposed to do. Anyway, you see the picture of what we're going to get, but let's just try it. Now this is a pretty extreme case. You see what we've got here is we've got a 0.1 kilogram mass that's doing the bouncing, and then we've got 50 kilograms on this. So we're talking about a 500 to 1 ratio here. That's the highest ratio we've done so far, and it's about what you need in order to make this thing work quite precisely. So let's try it. Sometimes starts there with some initial conditions. You have to say what those are. I put it a little bit off center when I started it. But all we're doing here is solving the simple equations of balls hitting each other, or a little ball hitting a wall and then hitting the big ball. So there is the simplest gas law right there. Two atoms, not 10 to the 23rd, just two, but it's only one dimension. Okay, so this is a rather extreme thing that's going on here. And see, I started off with sloppy initial conditions. I get a little bit of velocity, a little bit of off center, but you're getting a very nice sine curve there. Now you look at that sine curve with a magnifying glass and very high resolution, you see that it's got straight lines in there. You can't see that because the pixels are finer than the actual intervals of time that this has. Okay. Now, anytime you want to, you can go in there and push on the ball and give it an extra velocity and do stuff like that. So you can have a lot of fun trying different things with this. I'll just run through a few of the things that are interesting to see. So I'm going to pause this and get back out of there. Come back to this and go forward with this. So that's the first example. Now, check our numbers. That's the other thing that we have to do here. We check our numbers to see, and I started off here, as I said, with 50 to 0.1, that's 500 to 1 mass ratio, but in particular these things, with a velocity of 20 meters per second. Finally, we are actually using really minutes here, and then an interval y0 of 3.5. That's basically what we have right from there to there. And what do we get? We get a period here that's given by that constant, that is that constant with a 2 pi in front of it, mass ratio to that constant. Okay, stick those numbers in there, and I'm showing up here with 17.38 for the total period. Okay, is that anywhere near right? No, it's not. It's about square root of 3 times too big. What's wrong? What have we left out? Anybody got a chair? Yeah, yes? Why is that so big? If you don't answer it now, you're going to have to answer it on the homework. That's what you're going to do, is figure out what it really is. But how do you do that? What's the next step here? Is it really right for me to use blue lines to represent the velocity of this thing? Is that logarithmic thing really right? Any ideas? We're in a research group meeting right now. You got to come up with what the hell we do wrong here.
So
We got $1 million for this thing.
you could run an
It's
experiment.
going to go down the tubes if we don't figure this out.
If one wanted to lean on the app, they could prepare an experiment to see whether the gas
Sure,
is cooling or not.
You can always go back and check that, but we've got what we've got. What do we got here that's wrong?
This assumption of being in only one direction, one dimension.
Let me hear that. I don't quite understand. When you say one direction.
One dimension, I meant.
Oh! I mean, I would quibble with that, but the experiment for this would really be difficult to do because it obviously would want to go crazy, right? To get it to do that perfectly. But that's an advantage of the numerical simulation. This is frozen to one dimension. So that's not the problem. If you were to actually do it in the lab, you're absolutely right, they'd be all over the place very quickly. Well, you can make you can make one of those superconducting tracks, right, and have little cars and things and do this experiment. You'd be able to have one dimension in that case. Now there's something else wrong here. Now remember, we have two kinds of things, right? We had the red and the blue, right? Is this a single whammy or a double whammy? Yes. With our logarithm, it's single, right? Logarithm single whammy. This is double. This is adiabatic. This is not isothermal. Now the ball isn't increasing the velocity very much. Okay, so it's pretty close to isothermal, but that ain't gonna fly. That's what's wrong. We got to use the adiabatic formula, and that's what you're going to do at home. See if we can get close to the answer. Okay? Does that make sense? I was kidding about the $1 million, but someday you're going to be somewhere where they're not. We got a lot of money flowing around this research in this lab. It's unbelievable what we've got. And we can lose it. Okay. Anything else I need to say here? This is another one to play with. Here I'm getting pretty extreme with the thing, but I'll let you play with that. But there's where I actually stated. We're a simulation of an adiabatic case in all of these. Now, actually, we've been talking about fixing it. We could fix this thing so that the whatever it was took away whatever velocity it had.
We would have to decide on how that energy is bled off during the bounce. But we should be able to.
And our first step would just do it artificially. Just say, I always want this thing to have velocity, you name it.
Infinite pool of that same
right.
temperature.
And thinking of models of economy, this is what the Federal Reserve is supposed to do, right? When the economy heats up, they're supposed to cool it a little bit. And when it gets cold, it's supposed to heat it. Unfortunately, that really doesn't work very well all the time. We've had plenty of examples of that fail. Anyway, as you look through these examples, and this one is getting really pretty tight here, this one is pretty monstrous. Still looks pretty good as a sine curve, but you should probably notice that it's drifting a little bit, and the various phase. There's a little bit of a drift. If you draw a line through that thing, you see that it's not centered very well, but that's pretty extreme. Okay, we're talking about, again, a 500 to 1 mass ratio. All right, now let's have some fun with this stuff. Real fun. This gets to be really crazy here. But it's also interesting because this is something where you get, just using this classical bouncing model, really simple one, with a virtually infinite ball. This is, now the ratio is 5,000 or more to 1. You get to see what I call a classical introduction to Heisenberg quote-unquote uncertainty relations. Here's our formula, which we derived, okay, for the velocity, and this is the red case. This is the adiabatic. That velocity is going to go up like mad here, okay? And basically what you're seeing here is a product of the space allowed and then the velocity within that space, okay? And what I'm saying, that's analogous to what we call an uncertainty relation in quantum mechanics. The uncertainty of position times the uncertainty in momentum is some constant with an integer attached to a very famous constant, Planck's constant. But forget that, just call that a constant for now, and realize that if I am going to have a ball closing in on, and this is now one victim here, okay, as I close in on this thing, each time picking up twice the velocity of the ball. Remember, we add 2v2, 2v1 to each collision that we have with the ball, regardless of what the little ball is doing. So the big ball comes in at a velocity and maintains that velocity of 1. This is time. This is distance in whatever unit gives a 45-degree slope. And the idea is that we start off with a delta x, that's the space right here, of 3, okay? And it's going to close in until it's 2, until it's 1, until it's 0. But what's going to happen in the time that you're getting to 0 is this thing is going to go back and forth faster. Well, I should say faster, with going no speed at all. Then it got 2 times the v1 added to it. So there's velocity of 2 right there. You can see the slope is 2 to 1. And then it comes back with a slope minus 2. It's hit again, picks up 2v1, v1 is equal to 1, so it picks up another 2. 2 plus 2 is 4. And now has a velocity of 4. And then it goes back with minus 4. And then it gets another one, and with another 2, it's 6. And then minus 6. And then 8, minus 8, so forth, blah, 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 okay? That's what you're seeing on these pictures here. And what's really interesting is if you extend each of those velocity profiles, if you extend this guy out to here, all the lines meet at 2 points. Isn't that queer? That's queer, right? But that's just geometry. That's the kind of geometry that we were kind of touching on when we were talking. We'll see more of it later on. So this is what I call the classical monster mash. Okay? And so much else I could say about it. But the basic idea is that you have a big space, you have low speed, decreasing the space increases the speed according to, and this is the way Feynman really likes to describe the uncertainty principle, is as you close in on a thing, momentum grows. Now, you say, what the hell? These are particles. Quantum mechanics is waves. But waves do that. You see, what you're doing is you're putting more and more Fourier components into what was a nice Gaussian, this sort of a small number of Gaussian harmonics, okay? And you're adding more and more of those and making bigger ones than the ones you already had. Keep adding that and adding, right? So basically, when you close in on a quantum wave, you're making a bomb. If you close in enough, you got a bomb that's going to explode, kill you. That's exaggeration, just to make you realize that you're really dealing with when you close in on this ball bouncing back and forth is you're making the thing mad. Okay? At some point it's going to bite you. All right, I want to show you some ways that actually do that, but this is just particles bouncing here. And what's really neat about it, and I guess we might as well just go ahead and animate the monster mash. Here we're talking, forget what the mass ratio is that I'm going to be showing here, but it's pretty big. So it hits the ball, okay? Ball picks up 2 times whatever that velocity was. The big mass hasn't changed at all. So there goes a little ball to hit the wall, or the ceiling if we were in a gravity-free environment. Comes back. Hey, big mass, here you are. Here I get another 2V. And another 2V. And another 2V. And it's really coming fast now. And from the energy reading there, we don't change the energy too much. So this was a differential equation that had enough delta t spaces to go and carry on the inverse delta x. The velocity went up as the delta x got smaller, and then it's back to being really slow now. Okay, so there's the monster mash simulated fairly nicely. Okay, and this is a picture of another simulation that isn't quite as nice. This one is a little bit better, but more symmetric, I should say. Okay, now I'm going to make sure I know what computer I'm on, and I also want to make sure I don't use up CPU. So I'm going to stop it.
We have a question.
Yes. Yes.
Is the velocity of the first bigger
This guy.
mass, right,
Right.
always less than the second small mass?
What did we get? Say,
Started
the
at
V1 here started out with, it started out with 10 to the minus 4 times 10, so 10 to the minus 3 centimeters per second, which that's what you saw sort of creeping. And it's a huge mass, so that didn't change very much.
Okay, so
Until
my
it got
question
to,
is that when you say single or double whammy, when
this is definitely a double, because there are 2 things that are happening here. First of all, the time to go between bounces is increasing, right? But so is the speed, you see. So that's what we mean by the double whammy, is that the speed increased due to just having a smaller space. And then on top of that, because this thing had velocity and added that velocity times 2 to the little thing every time it hit, 2, add another 2, add another 2, add another 2. That's the second whammy that goes along with the first whammy, which is just making a smaller space, right? And not letting the speed go up. That's the isothermal.
But when you
This
say
is
small or large velocity for the second mass, it is just with respect to itself, right?
Well,
Because it's always higher than the velocity of the first mass. But if
Actually, we started this one off, if you're talking about this is first and that's second.
No,
I'm
M1
usually
and 2.
calling this
Yeah.
the first
Yeah.
and that the second.
Right.
We started off with the second one, nothing. So it came in and just hit it and it took off with a
Right.
release.
After initial condition,
Yes, after
um,
you,
my point is that when you say small velocity for V2 or high velocity, is this with respect to itself or the other mass?
well, all of the velocities that we're measuring are with respect to what we call the laboratory.
Right.
That's the graph there. So the difference between measuring that velocity from the laboratory's point of view and what you're maybe referring to is what does the ball see as a relative velocity? Obviously, since the ball's going this way, when it comes back, there's a little bit of additional velocity that it sees for that little guy, right? But we haven't, at this point, I don't think we really care about that difference, simply because this thing is so slow. Is that answering your question at
And
all?
eventually, M2
My-
will end up going faster because, for example, the last question on this homework set that was going to be due Wednesday is the game over situation.
Mhm.
So at the point when M1 is suddenly going faster, M2 will never be able to catch up to it.
Right. There's got to be a last collision in that problem
Yeah.
where he'll go up to the ceiling and he'll get some velocity, right? But if that velocity is less than what that big ball has, you'll never catch him. Never catch him. That's the game over. Is that-
Let me ask my question another way. So, my point is that part of the process is adiabatic and part of it is isothermal.
I would question that might be a confusing way to look at it, simply because once I don't have that, whatever it is, the Federal Reserve cooling, if I don't have built into the program a cooling of little m2, okay, so that m2 is never going more than v2 that he started on the first go, right? If I make that always the same, okay, that's equivalent to making the temperature for m2 always constant, not taking it up, not making him have any more speed than he started with. So in you go, right, and the big ball says, oh, that's a nice, cool little guy, not hurting me much, okay?
Which means isothermal.
But, yes, isothermal, right? But as the time between the hits goes up, even though the ball hasn't increased in speed, this thing is still going to feel the force, right? The isothermal force, right? Which is a lot less. You saw how it's more gentle than the adiabatic. You have one inverse y cubed, right? You come in there, you're boom at y equal close to 0, right? Whereas you go to 1 over y, that's not going up very much. That's the isothermal, right? Yes.
So I have a question. The M1 mass is going backward due to the M2 having enough force to hit him back, or
Yes.
the space
Yes.
between them is so small that it's going
It's a
forward?
little bit of a cheat on this right here because we've got a wall, right? And this guy right here has a potential
Thank you.
also with respect to that ball. So you probably saw when we were at this extreme region in here, the little one was just buried in the big one. So we're then feeling the potential that we've put into whatever the balls in the walls have, right? So at that point, this never got to infinity. It didn't have to. It came off. It got enough momentum to be sent back.
So it's the small ball that's hitting him back, not the wall. bouncing.
At the
Right.
end, both do.
It's both,
It's both.
yeah.
Play it again.
Yeah,
It'll
play
be
it
a little more
again,
apparent.
Sam.
If our graphics are a little tighter, you
Yeah.
can see it shredding the ball when it's pinned up against the
Yeah, see,
wall.
here he comes. The little ball doesn't have any speed now at all. And that means it's at absolute zero if it was isothermal, right? Well, he doesn't stay at absolute zero. Now he's already got some speed, right? He picked up basically twice the speed of this guy. All right. So now he has two, the ball has one, and that never changes much until we get the two of them on top of the wall. Okay. So he comes back with his measly 1.1 centimeters per second. That's going to change now. Okay.
Just about 0.4.
Now this one changes a little bit, but hell, it's in the fourth place, right?
Now it's about 0.6.
0.7. At this point, he's buried. So most of the rules that we've been writing are not applicable at that time. But we'll take our momentum any way we can get it, because I'm Mr. M1, I want to get out of here. So he got out a little early.
And in reality, if you had more particles, you would see a little bit more that it's actually
If
that
you
the
had,
force can actually be
if you had
causing
little-
it to move
little
back.
if you had a smaller particle, make it a pixel-sized thing, and it wouldn't be very impressive. But this is enough just to show the basic idea, I think. So this is very adiabatic, not isothermal at all. I mean, that speed goes crazy. This guy's taking off. Okay. Okay, any other questions about this? We've got some more crazy stuff to show you. We've got about 10, 15 minutes to do it. And the stuff you can play with on your own, that's the other thing about what we've got here. Okay, let me pause this. And thank you for the questions. That's what we need in a course like this. And are there any others? There will be if you get through what we're about to do here. And probably on your own you could, I find it's a beautiful geometry. Just take the single one and expand it.
Prepare that scenario.
This is just having a flat wall, but then have two balls coming in, double monster mash here. So there's two balls coming to hit. You have the same basic idea without too much difference. And the geometry is very interesting to study this. You can extend the things up into here. See, and they're the same curves here, just mapped over into that thing. But these, I should say, these are the same as the ones that we were working with before, just mapped into a different triangle. It's a very stunning piece of geometry, and it's one that is. This is a wave thing. This is we're now doing some quantum mechanics here, just briefly, for getting ready for wave mechanics, which we will do a little of in Unit 4. But you ought to see this. This is very stunning. We were lucky to discover this. This is something that I'm sure Bohr would have been fascinated by if he'd had a Mac and could simulate what happens if you take the simplest Bohr problem, the Bohr of a single particle wave on a ring, an atom that is just a ring. Don't worry about the radius at all. It's like a Rydberg state orbiting around a circle. Okay, but this is really a circle. This is just a wave function, sine and cosine of some angle phi, wrapped around, and this is the wraparound unrolled here, and this is going to be time this way. Okay. Now you all know that if you start off a Gaussian wave, in quantum mechanics they show you the Gaussian just sitting in a plane, no force field or anything, that Gaussian wave, because it has many Fourier components, has momentum in it. It's a little bomb, and if it's a very tight Gaussian, it's a bad bomb. But if it's a little a gentle bomb, okay, it explodes, but it does it very gently, okay. That means you just get a Gaussian that's fatter and lower and fatter and lower. Probability doesn't change. You've all talked about that in quantum courses before, right? Well, what happens if you take that situation and wrap it around so as they expands, it runs into itself on the other side and interferes? That's what this pattern is. This is a fractal pattern made by the simplest problem in quantum mechanics. One-dimensional ring. Okay, that's what you see as time goes on. What is this? That's what it took me a long time to figure out something about this. So I'll go ahead and I'll start the simulation up here if I can get away with it. Let's see if I got it here. I think this is going to do it. It's got a little finger that says it wants to go. Okay, I think it's going to go. Oh,
All right, just pull it from this scenario. That had been replaced in an
Oh,
earlier
that
paper,
was-
but it didn't get copied over.
okay. I'll just
Sorry about that.
I'll just go ahead and use the other one and take it to second. Let's go over
Functions in
to
L3.
this one right here and see if you think that one would be the same though.
It's a broken link. Go to the control panel
Okay,
and select the scenarios from the buttons.
I've got to get to that though. This is just a picture of the thing, I think. Let's see if I've got that right here. That's what it's supposed to do, and let's just see if I can get it. If I click here, I get scenarios. Is that what you're saying? No, that's probably not what you're saying. Forget what was it. I've got to. It looks like it's.
Launch it and then go to
It
the
looks like it's a
control.
legitimate.
Yeah, but it's
link.
different behind the link.
Let's see.
It's visible.
No, we just get wave it.
And scenarios, right there.
Oh.
Nope, that one.
Well, scenarios
You
are.
scroll all the way down.
Maybe I can.
Right there at the bottom it says boxcar and Gaussian. No, up. There you go. Choose which one you want.
We want the Gaussian redistribution. Let's just see what that does. Okay, there we go. There's the thing. Expanding on the ring and running into itself on the other side. And those are the Fourier components of the Bohr thing. So we've got everything up to quantum number 15, and then we don't have anything above that.
It plays pretty quick compared to the air.
Yeah, this is a fast computer for sure. But you can see every once in a while it shows something that has triple symmetry, then five-fold symmetry, and seven-fold, nine-fold, and so forth. And the fractions there, and then all of a sudden it reforms on the south pole.
Switch it back.
That means I could probably get this one to go too. It's a fairly fast computer. Let's get it to do the wave it thing, and then go to scenarios and pick off the same thing, Gaussian with distribution. So there's a distribution up to about 15 or so. Started out with a Gaussian at the North Pole. It's anything but that right now. And you can see the actual wave forming down there. Then you start to see structure at a certain point. These phenomena have funny names. Quantum fractals, all kinds of weird names. Revivals, that's the name of a different effect that occurs when you start a laser up, and that was discovered by Joe Everly in about 1979 or so. And since then it's been expanded on somewhat. But this is just simple Bohr quantum mechanics of a particle on a ring. And look at all of the structure that it produces. It's really quite beautiful. So wherever you see a dark region, that's where the particle is. Wherever you see a light region, that's where it's not. It's where it gets to be very close to zero for quite a distance. One of the messages of this is that the thing that's amazing about quantum theory, and the thing that you should quantify it with, is where the particle is not tells you what's going on. It's like the Sherlock Holmes Hounds of Baskerville, right? It was the fact that the dogs did not bark that solved the crime. Because the dogs know the owner. The dogs that do not bark tell you what's going on. It's zeros that really
Coming up to
show
another interesting
where
point here.
waves are. These are coordinates in a funny kind of way, or what's going on in a very simple quantum mechanical problem. Particle moving on a ring.
Bill, you've sort of gracefully windowed your frequencies there, and they give you a really nice profile on your pulse. I noticed something else in your control panel.
Let's go ahead and mention that. We'll mess it up. Let's go back to the scenarios here, and I think we've got what the laser jocks call a boxcar.
It's just a crude window there, right?
Yeah, just put all of the frequency components the same.
And cutoffs.
It goes crazy. It does not like that. But still, it's telling you something. That compared to this, I mean, you see a little bit of this left over, but when you put a square Fourier distribution, you're really asking for madness.
Don't they use frequency combs for high resolution spectroscopy and timing? We see a much more structure in here with this comb.
This is a very tame frequency comb. Those frequency combs have trillions of lines. Yeah. So these are the two really bizarre things that waves do, and make the same kind of lines that the monster mesh makes. So there's this analogy between the monster mesh, which is a bunch of lines with quantum slopes, and these guys, which are a bunch of lines with quantum slopes. You get to see them actually. Okay? Does this make it a little more interesting? Well, there's more after this, but we're going to save that for later, I think. You go ahead and study on your own. There's some neat things in there. If you have children that are learning fractions, how many people have children in this lesson? 1, 2, 3. Any more? Well, that's enough. You've got your hands full, right? Do you want your kids to be interested in science? You want to show them things that are really cool to play with? There's something here where you study fractions by plotting the numerator versus the denominator, and you get the stuff by doing that. It's very cool.
It's sort of a segue. You're taking a grid of integers and projecting the rational numbers. Projection is a powerful tool. And you'll see it really well here in this.
The best thing I can do is just fast forward here. Show you where this is. It's at the bottom of it.
We get a lot of material in this lecture.
Yeah, here's where you're plotting numerator versus denominator for all numbers.
Integers.
You're trying to find the rationals in the real line. The real line is at the top. And you just draw a couple of circles, find their centers, draw them again, find their centers, color them in sometimes, okay? And you make what's called the fairy sum tree. These are fractions that are lined up in a very descriptive way. And each one of the circles up there corresponds to one of these resonances that you have on the sides here, basically a fraction. Each fraction here represents whatever you want to call it. We haven't really given very good names to these things. But that's a good way to see where the fractions are on the real line. It's invented by John Ferry, was a geologist in 1815 who was studying the tides, resonances of the Bay of Fundy in Newfoundland, which has huge tides, but also has all sorts of harmonics, and he was able to use these numbers here to predict a few of the harmonics. That's 1815, and then it isn't until 1930s that Ferry, the other guy, I can't think.
Ford.
Yeah, that is Ferry, comes along, and Ferry's sum is.
We have some links in there if you're interested.
Yeah,
in looking
there
back.
are lots of links.
It was a hot time in math.
Yeah, but this makes getting fractions fun. Just do up to a quarter, right? You know, and draw the circles for that. And it's described how that works. And Ford is the name of the guy that came along in the 30s and got the geometry going on this. So for a long time, I didn't know what the hell this was. It was just fun. But it gets more fun when the mathematics starts to settle out. It's nice to have both the mathematics and the physics working for you, right? Don't just take whatever the computer gives you and go home. Try to figure out if there's some way that you can make sense out of what the computer's giving you. Maybe then you make some sense out of that experiment that's going crazy. Okay. We'll see you on Wednesday, and we'll talk about potentials and force geometry.